Hello there, and welcome to our last lesson in astronomy. In this lesson, we're going to learn about how stars have kind of a life cycle where they start off in one condition, they become a star, and then they end up in an end condition, and that some of that matter can be recycled, and this cycle can continue. So that's what we mean by cycle, that there is some connection from the life of one star to the life of another. And then we're also going to learn a little bit about some of the evidence that has led scientists to come up with the Big Bang Theory. So the life cycle of a star begins in the same place. They all start in the same way, as a big cloud of gas and dust, and these big clouds of gas and dust are called nebula. This picture here is of a famous nebula. It's called the Horse's Head Nebula. It's really pretty to look at. I guess it kind of looks like a horse, maybe a seahorse. I don't know. Kind of put some ears here and like kind of something like that. Yeah, so the Horse's Head Nebula, there's all sorts of nebulas out in our galaxy, and they're just places that have lots of gas and dust, usually the leftovers of older stars. So in order to end up with a star, you need, of course, a lot of matter, and those nebula are full of hydrogen and helium that will be the building blocks of a new star. And so at some point, the dust and gases in the nebula start to sort of coalesce around each other, usually by static at first, and then by gravity as it gets bigger and bigger. And you'll have this sort of blob of gas and dust that's growing and growing that they call a protostar. So this could be considered a protostar. I drew it as sort of having a glow, but it doesn't. There's no glow yet. It's not a star until there's enough matter and gas and dust packed in there that the gravity starts to increase the temperature and pressure in the center, that core of the star, and eventually gets hot enough and high enough pressure that hydrogen starts to undergo a nuclear reaction and turns to helium, and that's what gives off the light from the star, and that's when you have a new star being born. So once the star is born, it will exist until it runs out of hydrogen fuel. And the bigger the star, the more intense the pressure and the heat. And so bigger stars actually don't last as long because they're going to burn hotter and faster. So Rigel, one of our friends from the Orion constellation, is a big blue supergiant star, and it has a life of about 10 million years. And our sun, which is more average and cooler and smaller, has a lifespan of about 10 billion years. And Alpha Centauri, which is our nearest neighbor here in our galaxy, has a lifespan of about 200 billion years. So the smaller and dimmer and cooler your stars are, the longer they will last and burn because they're not consuming their fuel as quickly. At the end of a star's life cycle, what happens is there becomes an imbalance in the core. So throughout the life cycle of the star, there's a nuclear reaction that causes outward pressure as all this energy is being generated by that nuclear reaction. And then there's inward pressure due to all that gravity that's being crushed in there all at once. And so as the star goes through its life cycle, those two forces are pretty much in balance. But at the end of the life cycle, the forces outward start to diminish, right? The reaction starts to slow down because there's not as much hydrogen present. And the core of the star starts to collapse. Collapsing core, right? And so as it starts to collapse inward, some of those outer layers of the star start to drift away from the core, and you end up with a cooling effect. So they appear more red, and they become what you call a red giant. So red giant because it's much bigger than before. So this will happen to our star in about 5 billion years or so. The outer layers will swell out and actually consume the inner planets, like way out beyond Mars. And the center part, the core of our star, will collapse into a smaller volume as the gravity starts to crush it all together. So as the core of a star collapses and the outer layers start to expand away from it, there are basically two fates that a star can have. For most stars, they'll swell up and become red giants, and then those outer layers will just drift away and they'll become what's called a planetary nebula. There'll be a whole bunch of dust and gas that just drifts away from that central part where the star was out into space. And they're really pretty to see if you have a look at planetary nebulae. Just Google that. You'll see there's all sorts of cool images that produce planetary nebula. And then what you're left with after all those outer gases drift away is just the collapsed core, and that we call a white dwarf. And that can exist that way for, millions of years as well, as it just cools down over time. Now, for the really big ones, and these are fairly rare, they swell up and become really, really big. And instead of just slowly allowing all these gases and dust to drift away, there's a dramatic collapse that happens in the core that rebounds a bunch of energy outwards, and you get what's called a supernova, which is this really intense explosion where those outer layers get blasted away out into space. And all sorts of elements that aren't made inside of stars normally get formed in that intense explosion. So lots of the elements that make up our planet were made by older stars that underwent this supernova explosion and produced those heavier elements. All right, and what you're left with is the collapsed part of that really big star, which can be either a neutron star, which is this really condensed, packed ball of neutrons out there, or a black hole where you have enough matter collapsed in the center there that the gravity is so great that not even light can escape. So those are the options for what happens once the core of a star collapses. And then of course all that dust and gas that either floats away during a planetary nebula or blasted away during a supernova, that can become new stars when they form again from a nebula made of those gases. So a little recap here. We're going to start with a nebula, and then we will produce the protostar, which is that blob of gases as it starts to condense, and then you'll get a star. And then if it's a lighter star, like less than 20 solar masses, that sort of thing, as it goes through its life cycle, eventually it'll get to the red giant phase, where the outer layers float away and the center collapses. And then you'll have a planetary nebula, and then you'll eventually end up with a white dwarf. And for the really big ones, heavier, 30 solar masses and up, that sort of thing, you get a red super giant. And then at some point it'll go supernova and explode, and what's left in the core will be either a neutron star or black hole. Great, so hopefully that makes some kind of sense, and all these gases here can then cycle back and become part of a new nebula. Okay, now if you look out into our galaxy, what you see are groups of stars that originate from the same nebula. So nebula can be massive and expansive and contain millions of stars, or they can be smaller and only have a few thousand. And so there's a couple terms that are used to distinguish those. So the smaller ones are called open clusters, and the massive groups are called globular clusters. And really all a galaxy is a whole bunch of those clusters of stars held together by some gravity at the center of the galaxy. And so there's different types of galaxies. You know that ours just has that kind of spiral shape, which is really cool, but they're not all spiral shaped. Some of them are more blobby and have different types of shapes. So a fellow named Edwin Hubble, about 100 years ago, got a job working at the Mount Wilson Observatory in California, which you can still visit today. This picture came from their website, and this is the Hooker telescope. And back in 1920, it was the biggest telescope that had ever been built. And what Edwin Hubble discovered using this telescope was that there were a lot more galaxies than just ours out in the universe. And so it made our place in the universe a lot smaller. There were billions, as many galaxies out there as there are stars in our own galaxy. So this radically expanded our understanding of the universe. The other observation he made that changed everything is that all those other galaxies seem to be moving away from us. So how would he tell if they're moving away or toward us? Well, it comes back to those spectral lines, those lines that helped us to be able to identify the different elements that were there in the stars. And so if the object that was giving off that light was moving closer to us, like if they were accelerating toward us, that would mean that all that light would be shifted towards the blue end, right, of the spectrum. And then if light is moving away, it is shifted towards the red end of the spectrum. And what Hubble found was it didn't matter which way he looked with his telescope out into the universe, but all the other galaxies were all moving away from us. There was this expansion that seemed to be going on. All galaxies are moving away from us and from each other. So we're not necessarily the center. We're just part of this expanding universe where all the pieces are all spreading away from us. And so with this observation that everything is moving apart, you can easily see how they would be led to the conclusion that, well, if it's moving apart now, if we go backwards in time, that means everything has to come together, and eventually there'd be a point in the distant past where all matter would be in a single spot, a single point. And so that, and a bunch of other observations, of course, that definitely would occupy a lot more than one slide, led them to the idea of the Big Bang Theory, where everything was at a single point and then exploded from there. So I hope you found that interesting. We'll see you soon.